So in this video, we're going to go through a number of equilibrium problems, true-false questions, multiple choice, a few free response questions at the end. These will cover a range of topics, theory, as well as Le Chatelier's principle. So the first page here has some true-false questions on it. Pause the video and try to answer them yourself. So a dynamic equilibrium is reached when the forward and reverse rates are reactions occur at the same rate. Of course, that's the definition of equilibrium, so that is definitely true. But number 7 says that for a system at equilibrium, concentrations of reactants and products have to be the same. That is definitely false. That's a little bit of a distractor. It's the rates of the forward and reverse reaction that are equal, not concentrations of reactants and products. Think of ice tables that you've done. How many times have the reactants and the products had the same concentrations on the equilibrium line of an ice table? That almost never happens. Equilibrium can only be established in an open system. That is false. It happens in a closed system. If gases are involved, then it must literally be a closed container, so the gases can't escape. If the gases escape, then there can't be a forward or a reverse reaction. If it's an aqueous equilibrium, then the water itself in which the substances are dissolved is usually considered to be the closed system, since aqueous species can't escape from the water. The value of Kc for a reaction can be used to judge the rate at which equilibrium is attained. That is definitely false. Kinetics is totally a separate issue from equilibrium. You can think of it this way. The size of Kc will tell you how much product you can make, but it tells you nothing at all about how fast you'll make it. The activation energy, which is from our kinetics unit, it will tell you how fast a reaction is. The larger the EA, the slower the reaction, but it tells you nothing about how much product you'll eventually have made. So equilibrium tells you how much product you can make. Kinetics tells you how fast you can make it. Number 10, if QC is greater than Kc, the reaction's not at equilibrium. That is definitely true. Q is the reaction quotient. And not only does this mean it's not at equilibrium, but it means that the reaction would shift backwards to reach equilibrium. When Q is less than Kc, the reaction shifts forward to reach equilibrium, and if Q were equal to Kc, then we're actually at equilibrium. This next question, which of the following graphs shows the rates of the forward and backward reactions when hydrogen and iodine are mixed? We'll assume that they're making hydrogen iodide HI. Pause the video and see if you can select the answer. The best choice here is answer A, because it shows all four graphs show the forward rate decreasing and the reverse rates increasing. That's true because the reactants, hydrogen iodine, are getting used up, so the forward rate decreases as the concentration of reactants decreases, and then they're forming products, and as the product concentration increase, so does the reverse rate increase. However, choice A is the only graph that shows the forward and reverse rates becoming equal, and they become equal when you've reached equilibrium. 37-38 deal with manipulating chemical reactions and the relationship with Kc. In number 37, we are looking at taking a reaction and doing two things to it to go from this reaction to this one. What have you done? You have reversed the reaction, and you multiplied the equation by 1/2. Now, when you reverse an equation, Kc is the reciprocal of the old Kc. That's because what used to be products are now reactants and vice versa. When you multiply a reaction by some number, in this case by 1/2, the rule is that you raise Kc to the power of the number you multiplied by. And that's because the coefficients become the exponents in the Kc expression. So in this case, we can say that the Kc is going to be 1 over 6.1 times 10 to the minus 3, and then to the power of 1/2. So to raise something to the power of 1/2 is to square root it. the choice here that matters is C. Now, just a note about these questions we're going to see. The author of these questions includes the units in the equilibrium constants. We ignore the units in our course, so you can just ignore those units when they apply to equilibrium constants. Note that the author is using the symbol dm3 to represent cubic decimeter, which is the same thing as a liter. So when you see moles per cubic decimeter, like we see there, you can think of that as moles per liter. Number 38, we're given two equations, A becomes B becomes C, and we know their equilibrium constants. What's the value of Kc for this reaction? 2C become 2A. Alright, this question's a little bit more involved. First of all, we want to treat this sort of like a reaction mechanisms question. I'm looking for the equation 2C becomes 2A, and I'm going to see how I can obtain that by manipulating the two equations earlier. So the first thing I'll notice is I want two C's, and I want them as a reactant. Reaction number 2 had C, but it had it as a product. So if I take reaction 2 and reverse it, and multiply by 2, I'll get 2C becomes 2B. Since I reversed it and multiplied by 2, the equilibrium constant here would be 1 over 0.01 squared. Right? The old Kc was 0.01, so reversing 1 over 0.01 and multiplying by 2, 1 over 0.01 squared. The first reaction, A becomes B, we also need to reverse because we want A's as products. And we wanted two A's, so we're going to have to multiply it also by 2. So we'll get 2 B's becomes 2 A's. And again, we reversed and multiplied by 2, so 1 over 2 squared is the Kc for that. Notice the B's cancel, and we're left with the equation we want. 2C becomes 2A. Now here's the new thing. When you add equations together to get an overall reaction, the Kc of the overall reaction is the product of the Kc's that were for the equations being added. So 1 over 4 times 1 over 0.01 squared is going to be 10,000. So 1/4 of 10,000, answer A is the best choice. So notice that we learned a new thing in question 38, or saw a new concept, and that is that when you add equations together and get an overall reaction, you multiply the Kc's for the equations together. Number 47, pause the video and try it. Consider the following equilibrium system. N2O4 becomes NO2's, Kc is given. We have 0.5 moles of each substance put into 1 liter container. And whenever I see moles, I immediately look for volume, because I need to use C equals N over V to convert to concentrations. Here the volume is 1 liter, so the numbers are the same, 0.5 molarity, 0.5 molarity. Which of the following describes the changes in concentrations as we go to equilibrium? Well, this is a question that's going to be about finding Q. Q is the reaction quotient, and in this case it's concentration of NO2 squared over N2O4. If we calculate Q, we can compare it to Kc to decide the direction the reaction will go to reach equilibrium. So 0.5 squared over 0.5, Q is equal to 0.5. But Kc was 4.5. So Q is less than Kc, which means the reaction has to go in the forward direction. When Q is less than K, we go forwards, and that means the reactant N2O4 will decrease in concentration, but NO2 will increase. So N2O4 decreases and NO2 increases. Choice B is the best answer. Number 49 looks to be a similar question. We've got 6 moles, 0.15 moles, and 0.1 moles, all in a 1 liter container, and they're allowed to reach equilibrium. Which of the following changes would occur as we go towards equilibrium? So similarly, we're just going to find Q and then compare it to Kc, and then hopefully see one of those choices down below as the right answer. Now, it is possible, if we just look at these choices, because I just noticed these are worded in a slightly different way, we might be able to answer this without even finding Q. Notice in choice A that it says that the C3H6O increases while the H2 decreases. But those two things are on the same side of the equation. They're both on the right-hand side. If you're on the same side of the equation in an ice table, both substances there would have to either increase or decrease. Think of the change line. They're on the same side, they'd have to both increase or both decrease. It's not possible that one of those would increase while the other decreases. Choice B, C3H6O increases along with hydrogen. That's at least possible. Choice C, the C3H8O, which is on the left side of the equation, and hydrogen on the right side both increase. Well, that's got to also be impossible, because if you're on opposite sides of the equation, one will increase while the other will decrease. They can't both increase if they're on opposite sides of the equation. Similarly, choice D is impossible for the same reasoning. So without even finding Q, we could jump in and argue that B is the best choice based on the logic of filling in an ice table. Which of the following graphs represents hydrogen concentration after equilibrium has been established? It's a little bit of a trick question, maybe, but maybe not. If we're after equilibrium has been established, the concentrations of everything, including hydrogen, stop changing. So choice B shows the concentration not changing over time, constant. Therefore, choice B is the one that would represent after equilibrium had been established. Which of the following reactions is consistent with the above graph? Notice that the graph has one substance decreasing in concentration and two substances increasing. That matches all four of these choices. They all have one reactant, so one thing decreasing, and two products with two things increasing. The way to distinguish this is to look at the changes that occur. If we consider the reactant, it started here and it reached equilibrium here, so it changed by this amount. Let's call that X. If we look at the two products, we know that they both started at 0. One of them increased to here, which is the same amount, so we'll call that X also, while the other one increased like this, and that looks to be 3 times as much, so 3X. So we can see now what the ratio is for the reactants in products. The reactant has a coefficient of 1 for a product with coefficient of 1 and another product with coefficient of 3. It's a 1 to 1 to 3 ratio. So looking at the choices, choice B is the only one that shows that ratio. Which of the following is not a condition necessary for equilibrium? Well, as we said earlier, you definitely need to have a closed system so that the forward and reverse reactions can occur. You have to have constant temperature, otherwise Kc will be changing, and if Kc changes, you can't be at equilibrium. You definitely have to have equal and forward and reverse rates. That's the very definition of equilibrium. And as we discussed earlier, it's not necessary that the concentrations of reactants and products be equal. We've got some NO2 and 2O5 NO placed in a container and allowed to reach equilibrium. When equilibrium is established, it's found that pressure had increased. Which of the following combinations is correct as the system went towards equilibrium? Well, looking at the choices, we can rule out at least a couple of them, I think. If Q is greater than K, then there has to be a backward reaction. The reaction will shift backwards. So choice A is not possible, since it says Q is greater than K and there's a forward reaction. We also know that when Q is less than K, the reaction shifts forward, so choice D is also not possible. So without knowing anything other than that, we could now narrow it down to a 50% chance of guessing. But notice the key phrase in this question was that in reaching equilibrium, the pressure has increased. Everything in our equation was gaseous, so this was a homogeneous gaseous reaction, everything in the same phase, homogeneous. And notice that there's 3 moles of gas on the left, and there's 2 moles of gas on the right. Since the pressure increased on the way to equilibrium, the reaction must have been shifting backwards. 2 moles becoming 3 moles would explain why there's an increase in pressure. So therefore we were shifting backwards. Choice C is the only one where we go backwards. It would have been because QC was greater than KC. In an experiment, we've got 0.6 moles of SO2, 0.3 moles, and 0.6 moles of oxygen in SO3. So everything is initially present in a 1-liter vessel. That makes me, again, think I should calculate Q, right? When I know everything initially there, I think I should calculate Q. The system is allowed to reach equilibrium. Which of the following are correct as we approach equilibrium? So if we quickly calculate Q for this will equal, in a multiple choice I do tend to take shortcuts. I don't write the Kc expression, even though it's easy to make silly mistakes when you don't. The SO3 concentration is 0.6, and we have to square that over the SO2 concentration, which was 0.6, also squared. And the oxygen concentration was 0.3, and that's not being squared. So 0.6 squared over 0.6 squared cancels, and we're left with 1 over 0.3, which is going to be about 3 point something. 1 divided by 0.3, which means we're less than Kc. So Q is smaller than Kc, which means this reaction has to go forwards. If it goes forwards, the SO3 concentration will increase, and the other 2 concentrations will decrease. So which of the following is correct? SO2 has to decrease, so 1 is not right. Oxygen decreases, that's good. And SO3 increases, that's good. 2 and 3, so choice C is the best answer. Here's some more true-false questions. If the position of equilibrium lies close to the product side, in other words, the products are favored, in other words, there's lots of products when equilibrium has been reached, then Kc is small. That is false. It's the opposite. Kc is large when you have a product-favored reaction. When Kc is small, the reactants are favored. Equilibrium lies close to the reactant side. You make very little product, and you'll have lots of leftover reactants. When the concentration of a reactant in an equilibrium is increased, there will be a forward reaction. That is true. If you think of a simple reaction, A becomes B. If you increase the concentration of A, the system will shift forwards in order to relieve that stress. Number 9, at a constant temperature, increasing the concentration of a reactant causes K to increase. That is false. Kc is constant unless you change the temperature. For a given reaction, Kc can be changed only by changing the temperature, not by changing concentrations. Number 10, removing some calcium carbonate from an equilibrium system of calcium carbonate, calcium oxide, and CO2 causes a shift to the calcium carbonate side of the equilibrium. That's tempting. If you understand Le Chatelier's principle, you might have said true for this, but then you would have overlooked the fact that the calcium carbonate was solid. Solids do not cause shifts in equilibrium, so that's in fact a false statement. An increase in volume of an equilibrium system involving gases brings about a reaction that will increase the moles of gas. If you increase the volume, you will decrease the total pressure in the container. The system will respond by trying to raise that pressure, And to do that, it'll make some more gas. So yes, it'll increase the moles of gas as a result. That is true. For an equilibrium system with an exothermic forward reaction, so think of A becomes B as exothermic, so heat is a product in the reaction, decreasing temperature will shift the equilibrium to the right. If we decrease the temperature, I'm going to use a simplistic logic, the system would try to produce some more heat, and to produce some heat it would indeed shift to the right. That is true. That kind of reasoning is sufficient for a multiple choice question or a true-false question, but not for a free response question where a more detailed explanation would be required. Number 13, decreasing temperature will cause Kc for an endothermic reaction to increase. That is actually the opposite. When you have an endothermic reaction, raising the temperature causes Kc to increase. Decreasing the temperature would cause Kc to decrease for an endothermic reaction. This is the opposite for exothermic processes. Number 23, consider this equilibrium system, chromate and hydrogen ions, dichromate and water. This is one we saw in the lab. Chromate, we remember, is yellow, and dichromate is orange. A solution of barium nitrate is added, and barium chromate precipitate forms. If the barium chromate is precipitating, then we are essentially removing chromate from that equilibrium. Again, using simplistic reasoning, we could then argue that the system will shift to the left in order to produce some more chromate. So choice C and D is not possible. Since temperature did not change, Kc does not change. So A is the best choice, a leftward shift, and Kc is constant. We've got an equilibrium here with bromine, yellow-brown colored, forming colorless products, bromide, hypobromite, and then there's acid, H+, and water. The yellow-brown color of aqueous bromine would fade, so it's going to get lighter, on adding a few drops of what? Well, looking at that reaction, the color would fade if the reaction shifts forwards. Some of the yellow-brown would be converted to colorless. So the question is, which of these things would cause a forward shift in equilibrium? Choice A, if we're adding HCl, we're going to increase the hydrogen concentration. Increasing hydrogen concentration would actually cause a backward shift as the system tries to lower that concentration. So A is not correct. By the same logic, KBr is also not true because adding it would cause the bromide concentration to increase, and again there'd be a reverse shift to lower the bromide. C is actually going to be the correct answer, but you have to use a little bit of grade 11 solubility to understand that. Looking at D, it again has the same logic as A and B. Adding some sodium hypobromite would increase the hypobromite concentration and would result again in a backward shift. So A, B, and D, I know for sure all create backward shifts. That leaves C as the only other choice. Now, why does adding silver nitrate cause a shift forward? It would seem strange because there's no silver and there's no nitrate in our equilibrium. The answer comes from grade 11 chemistry solubility rules. You might remember that bromides, chlorides, and iodides, salts, are very soluble in water, except when they're bonded to lead, silver, and mercury. So when we add silver nitrate, the silver ions will precipitate the bromide ions, and as they precipitate, you are lowering the bromide concentration. The system will shift forward to produce more bromide ions. We've got an equilibrium, NO and oxygen making NO2, and we are transferring an equilibrium mixture of the three gases from a 1-liter container to a 2-liter container. So in a sense, we have simply raised the volume. Which of the following combinations describes what will happen as we reestablish equilibrium? So when you raise the volume, the total pressure in the container will drop. That's Boyle's law from grade 11 chemistry. Pressure, volume are inversely related. When the pressure drops, the system will try to increase pressure again, restore the pressure, by creating more gas, if that's possible. In this equilibrium, there's 3 moles of gas on the left and 2 moles of gas on the right. So to create more gas, to raise the pressure again, the system's going to go backwards, and in this case, we're going to shift to the left. As we shift to the left, we're going to be using up the NO2, so the moles of NO2 would decrease. Choice D is the best answer. Consider the following equilibrium which relates to this graph, which relates to this equilibrium system. Iron and thiocyanate are making iron thiocyanate. This is the equilibrium we saw in our lab. Delta H is less than 0 is saying delta H is negative, and that is saying the reaction is exothermic. If the reaction is exothermic, heat would be on the right-hand side of the equation. And so, which of the following actions would cause the concentration changes at time t? Well, we see that the iron is slowly increasing, the thiocyanate is slowly increasing, and the iron thiocyanate is decreasing. The fact that there was no sudden change, nothing rapidly increased or rapidly decreased, tells me that nothing was just injected or removed, so adding or removing doesn't look possible. Nothing here is gaseous, so pressure will not be affecting anything. That leaves only temperature. And if you think about this for a minute, if we were to increase the temperature, the system would try to cool itself down by shifting in the reverse direction. A forward shift produces even more heat. The reverse shift takes away some of the heat that we've added. In shifting reverse, we'd expect the iron thiocyanate to drop, as we see in the graph, and the other two concentrations to increase, again as we see in the graph. And again, their increases and decreases are slow over time. They're not sudden spikes or sudden drops, and that's because the reaction is shifting in response to temperature change. Consider this equilibrium. It's the Haber process, nitrogen and hydrogen making ammonia. Again, it's an exothermic process, so heat is on the right-hand side. Which of the following sets of conditions would favor the formation of product? To favor the formation of product implies we'd like to shift in the forward direction. Well, pressure, low versus high. In this assignment, that's implying increasing or decreasing the size of the container. If we want a low pressure, we're going to increase the size of the container. If we want high pressure, we're going to decrease the volume of the container. Now, since there's 4 moles of gas on the left and only 2 moles of gas on the right, and we'd like the reaction to shift forwards, then essentially we're decreasing the moles of gas. Now, why would the system want to decrease the amount of gas? Well, to lower the pressure. So why would it be trying to lower the pressure? Because we were doing the reaction under conditions of high pressure. So just thinking that through again, if we do the reaction at high pressure, the system will try to lower the pressure. To lower the pressure, it will reduce the amount of gas and shift forwards. That looks good. Now, in shifting forwards, we're also going to be producing heat. Why would the system want to produce heat? Well, to raise the temperature. And why would it be trying to raise the temperature? Because we had lowered the temperature. So if we do the reaction at a low temperature, it'll shift forward to produce heat. If we do it under high pressure, it'll shift forward to reduce the amount of gas. So D is the best choice. All right, in this question we're told that methanol can be produced by reacting carbon monoxide with hydrogen. 2 experiments have been done. In the first, CO and hydrogen were placed in a sealed vessel, and the reaction allowed to proceed at constant temperature. In the second experiment, the first experiment was repeated, but at a different temperature. And we have 2 graphs below that show us the amount of methanol produced over time for experiment 1 and 2. The results show that experiment 2 was conducted at, and somehow we have to decide which experiment was the low temperature, which was the high temperature, and also whether the forward reaction above is endothermic or exothermic. Well, how are we going to do that? This is a good question because it relates back to kinetics as well as equilibrium. The first part of the question as to whether experiment 1 or 2 is the hotter temperature, that can be deduced by looking at the shape of the graph at the beginning of the experiments. In other words, remember that in a graph of concentration versus time, or amount versus time, we can deduce the rate of reaction by looking at slope. In experiment 1, the reaction starts with a slope like this. In experiment 2, it starts with a slope like that. So experiment 2 began with a higher rate of reaction than experiment 1. So therefore experiment 2 with a higher rate must have been done at the higher temperature. So experiment 2 was done at a higher temperature, not a lower temperature. Now, was it endothermic or exothermic? Well, we know now that experiment 2 was done at a higher temperature, but look at the amount of methanol produced. In experiment 2, you produced less methanol than experiment 1 when you reached equilibrium. So raising the temperature in experiment 2 resulted in less methanol being produced. So raising the temperature, if we look back at the equation at the top of the page, raising the temperature must have shifted the equilibrium backwards. Therefore, I can deduce that heat in this equation is on the right-hand side, and therefore the reaction as written was exothermic. So the best choice here is going to be choice D. Choice D, if I can just see it at the bottom, I can't quite scroll down, so choice D is the best choice for that problem. All right, question 44, we've got methane water reacting to make CO and hydrogen, and we can tell here that delta H is positive, which means we're dealing with an endothermic process, so heat is here on the left side of the equation. What's the effect of a small increase in temperature on the rate of the forward reaction, the reverse reaction, and Kc? So we're going to increase temperature. Chemical kinetics tells us that when you raise the temperature, the rates of reactions increases. So the forward and reverse rates will go up. They're both going to be higher. So now we're looking at choice C or D then. However, we know that in an endothermic process, that reaction is more greatly affected by temperature change than the exothermic process. So notice that the forward reaction here is endothermic, while the reverse reaction is exothermic. So the forward reaction rate is going to be raised more than the reverse reaction because the forward reaction is endothermic. Therefore, we're going to end up with more products. With more products, then Kc must be larger. So choice C is the best answer. Remember that temperature change is the one thing that can change the value of Kc. So because we shifted forwards by raising the temperature, we ended up with more product at equilibrium, therefore Kc is larger. In which of the following systems would the position of equilibrium shift to the left if we increased pressure, but to the right if we increased temperature? Let's consider the pressure change. If we're going to increase pressure, the system will try to reduce the pressure by reducing the amount of gas. So we'd like the reaction to shift to the left. Let's see if that'll happen. In choice A, there's equal amounts of gas on both sides of that equation, so actually a pressure change there will do nothing to the equilibrium. So choice A cannot be correct. Choice B has 1 mole of gas on the left and 2 moles of gas on the right, so by raising pressure, we'll cause this equilibrium to shift backwards to reduce the amount of gas, so choice B is possible. Choice C and choice D are not possible because they have less gas on the product side, so raising the pressure there would cause those two equilibria to shift forwards to reduce the amount of gas. So looking at choice B is the only choice there which will cause a leftward shift when we increase pressure. Let's just verify that if we raise temperature, it would shift to the right. In choice B, we see the reaction is endothermic, so heat is on the left side of the equation, and when I raise the temperature, yes, indeed, the reaction shifts forwards to cool itself down. Number 45, consider the following equilibrium system. We can see it's again endothermic, so heat on the left. The temperature is lowered and the amount of chlorine changes by 1 mole. The word change there, notice, is ambiguous. It doesn't tell me whether it goes up or goes down, but I do know it changes by a mole. Which of the following combinations would be correct? Well, let's decide what direction the reaction will shift when we lower the temperature. If we lower the temperature, the system will try to produce some heat, so it's going to shift backwards. And now I can see that the chlorine is going to increase by 1 mole. It said it changed by 1 mole. Now we can see it increased because of that reverse shift. Looking at the ratios, the water would also increase by 1 because of the 2-to-2 ratio. The HCl would have decreased because it's on the other side of the equation, and it would have decreased by 2 moles because of the 4-to-2 ratio. The oxygen would also decrease, but only by half a mole because of the 1-to-2 ratio there. So looking at the choices, the chlorine will increase by 1 mole, so A or B is correct. The HCl will decrease by 2 moles. Choice B is the correct answer. Phosgene is manufactured by putting CO gas and chlorine gas through a bed of carbon catalyst, and the reaction is endothermic. Which of the following conditions would favor the formation of phosgene? In other words, would favor the formation of product. In other words, would cause a forward shift in the equilibrium. Low pressure or high pressure? Well, there's 2 moles of gas on the left and 1 mole of gas on the right, so if we want it to shift forwards, we'd be wanting to reduce the amount of gas, and that would be true if we had the system under high pressure conditions. So therefore, C or D is correct. It's an endothermic reaction, so if we would like it to shift forwards, we should do the reaction under high temperatures. Under high temperature, the system will try to cool itself down by shifting forward and removing heat from the system. So choice D is the correct answer. This question is a little bit more advanced. Which of the following graphs shows the effect of temperature and pressure on the percentage of ammonia in the equilibrium mixture? And we can see that this was an exothermic process. Therefore, heat is on the product side. So let's consider what happens. We've got to look at temperature effects, and looking at the graph, it's actually got 4 curves per axis system because each curve represents a different pressure. So the graphs are showing us 2 things. They're showing us how temperature and pressure affect the percentage of ammonia. Let's consider the temperature. If we increase the temperature, looking up at our balanced equation, raising the temperature would cause the system to shift backwards. That would reduce the amount of ammonia formed, so the percentage of ammonia at equilibrium should drop. So raising temperature should lower the percentage. Therefore, choice A and B are not possible because those graphs increase. Choice C and D show decreasing percentages of ammonia. The pressure effect can be deduced again by looking at the amount of gas on each side of the equation. There's 4 moles on the left and there's 2 moles on the right. So if we were to increase the pressure, the system would decrease pressure by reducing the amount of gas, and in this case would shift forwards. So under high pressure conditions, we would get a forward shift and we would get more ammonia produced. So under high pressures, we expect a greater percentage of ammonia. Therefore, choice D is best because the highest pressure curve has the greatest percentage of ammonia on that graph. We've got the equilibrium. PCl3 and chlorine make PCl5, and it's again an exothermic reaction, so heat is a product. Which of the following graphs shows the relationship of concentration time as we add a catalyst at time t? Well, catalysts speed up the rate of reaction for both the forward and reverse processes. Remember, if you look at a potential energy diagram uncatalyzed, and actually this was an exothermic process, so I'll drop it down like that. If you look at the effect of adding a catalyst, remember that a catalyst lowers the activation energy, so we'd get something like this. But it lowers the activation energy not only for the forward reaction, but also for the reverse. And it can be shown that the effect is the same on the rates of both. So catalysts have no effect on the equilibrium, so choice C is best because it shows no change in concentration over time as we added the catalyst. We've got the graph showing N2O4 decomposing to NO2, and we can see it's an endothermic process. Which of the following would have caused the concentration change at time t? So at time t, we look and see the NO2 is increasing, the N2O4 is decreasing, the reaction is shifting forwards. But there's no sudden increase. There's no spike or sudden decrease with a spike. We don't see anything jump up or jump down. That's a sign that nothing's being added or removed from the system. So the choice number 3 here doesn't make sense. The change in concentration of NO2 would not explain what we see there. Changing pressure might seem tempting, but if we suppose we were to decrease the volume of the container to increase pressure, well, decreasing the volume of the container would have caused a sudden increase in concentration of both substances. Then we would see a shift. Or if we raised the volume of the container, we would have lowered the concentrations, and there would have been drops just like that in concentration. We don't see that kind of change, so there was no change in pressure. The best explanation is simply a change in temperature. In fact, we must have heated the system up because we were driving the equilibrium forwards to make more NO2. So choice A is the best answer here. We've got C2H4 and water making ethanol, and it's again an exothermic process. Which of the following would increase the mass of ethanol in the equilibrium mixture? In other words, what would cause this equilibrium to shift forwards? Well, we just saw that catalysts don't affect equilibrium. It would make the reaction reach equilibrium faster, but it wouldn't end up with a larger percentage of product. Decreasing the volume of the reaction vessel would increase the pressure. The system would try to reduce the pressure by reducing the amount of gas, and indeed that's 2 moles to 1 mole. That would result in a forward shift, so number 2 is possible. Increasing temperature in an exothermic process would have driven the equilibrium backwards away from the ethanol, and we would have reduced the mass of ethanol. Therefore, the only choice there that makes sense is number 2, and so B is the best answer. Equal volumes of 1 mole per liter solutions of W and X are mixed. The reaction below reaches equilibrium quickly, and at equilibrium the concentration of Y is 0.4. What's the value of Kc? I bet this is a question where a lot of you felt you understood what you were doing, but perhaps made a silly mistake, and that's why it's a 3-pepper question, one where students will overlook something. Remember, every time in the lab when we pipetted 2 solutions into the same test tube, we had to stop and think, what's the initial concentration, because of a dilution effect. If you're mixing equal volumes of 2 solutions, then their concentrations will drop by 1/2. So instead of 1 mole per liter, they start at 0.5 moles per liter. There's no Y or Z in the container. At equilibrium, you have 0.4 of Y, So that increased by 0.4, that increased by 0.4. These lost 0.4 because of the 1-to-1 ratios all across the board. So 0.1, 0.1, and 0.4. So Kc is going to be 0.4 squared divided by 0.1 squared. 16 is the only answer that would make sense for that. So D is the best choice. Notice that in multiple choice questions, I don't pay attention to significant digits. I just jump in and get the answer quickly. But in a free response question, I would definitely be including a lot of zeros in that ICE table. We've got this equilibrium, iron oxide, carbon monoxide, making iron and CO2, and I noticed there a little strangely the iron is liquid, so this must be done at a high temperature. Which of the following actions would cause the equilibrium to shift to the right? If we add some Fe2O3, well, notice it's a solid. Solids do not affect the position of equilibrium, so no. Adding iron, well, it's a liquid. Liquids and solids do not affect the position of equilibrium, so no. Removing some CO, the system would try to make some more CO and shift backwards, so that would not result in a shift to the right. Removing CO2, yes, would shift to the right to make some more CO2. Now, in a free response question, your reasoning would have to be tied into kinetics. For example, in part C, if we remove some CO, we would say that the forward rate has decreased while the reverse rate remains unchanged. Therefore, the reverse rate is now larger than the forward rate, and there's a reverse shift. Removing CO2 in choice D, now the reverse rate is lower than the forward rate, and there's a forward shift as a result. The solids and liquids aren't found in the rate law because their concentrations are constant, therefore they don't affect the rate of the reaction. Calcium carbonate, calcium oxide, CO2, and again this is heterogeneous equilibria. There are solids and gases involved. Which of the following would cause the shift to the left? Adding solid, nope. Removing solid, nope. Decreasing the volume, that would raise the pressure. The system would try to lower pressure by reducing the amount of gas, and since the gas here is on the right, that would cause a shift backwards to the left. That's looking good. Increasing the surface area is tempting, perhaps, to someone who's thinking a little bit too hard about it, but remember that it's a solid. Solids do not affect equilibrium. Their concentrations don't change. So C is the best choice there. Initially, 30 grams of calcium carbonate put in a 2-liter vessel. What mass of CO2 would be present at equilibrium? The mass of calcium carbonate is really not that important here. What is important is that Kc is 0.1 from above. Therefore, that's equal to the concentration of CO2. So now we can use moles of CO2 as C times V. We have 0.1 times 2 liters is 0.2 moles. The molar mass of CO2 is 44.01 grams per mole, so if I take 0.2 times 44.01, we will get 8.80, which is choice C. The reaction below reaches equilibrium in a closed vessel. Which of the following actions would increase the mass of Cl2? And we notice it's an exothermic process. So we want to increase the mass of Cl2, so we'd like this to shift in the forward direction. If we add some solid, no. If we increase the temperature, the heat is on the right-hand side, it's exothermic. That would actually cause the equilibrium to shift backwards, so no. Decreasing the volume, that'll raise the pressure. The system will try to lower the pressure by reducing the amount of gas. The only gas is on the right-hand side. That would cause a reverse shift, so no. Adding something that would precipitate the manganese. If the manganese is precipitating, then its concentration is dropping. The system would try to shift forward to make more. That looks tempting. Notice again, we could explain that with kinetics. The choice there is that the manganese is decreased in concentration, therefore the reverse rate is lower than the forward rate, so there'll be a forward shift. Which of the following conditions would favor the formation of hydrogen? So we'd like this to go forwards, and we see that it's an endothermic process. The delta H is positive. So under low pressure, low temperature, high temperature, we see that there's more gas on the right side than on the left side, 2 moles versus 4 moles. So if we want it to shift forward, it's going to have to produce more gas. Why would it be producing more gas? To raise the pressure, because we were doing the reaction at low pressure. So choice A or B makes sense. What about temperature? To shift forwards, it would be consuming some heat, so instead of producing heat, it's getting rid of heat. Why would it be trying to get rid of heat? Because we were doing the reaction at high temperature, so choice B is best. Equal amounts of methane and water are put into a vessel allowed to react. After 10 minutes, the equilibrium has been reached. At that time, hydrogen is added and a new equilibrium established, which graph represents the methane and hydrogen in the mixture. Looking up at the top at the balanced equation, we notice that there's 1 methane for every 3 hydrogens. So if we look at the initial change, since the methane and water were put in the container, the methane is dropping, which makes sense, but the hydrogen would have to increase by 3 times as much as the methane dropped. So looking at choice A, just at the initial amounts of drop and increase for methane and hydrogen, that doesn't make sense. Choice B looks possible. The methane dropped a little bit, the hydrogen increased about 3 times as much. Choice C also looks tempting for the same reason. Choice D looks impossible for the same reason as part A. So now we've got the B or C. Now if we were to add some, what did it say? Some hydrogen is added to the mixture. If hydrogen is added, then both graphs show a sudden spike in hydrogen, but looking back at the balanced equation, adding hydrogen would cause a reverse shift. So the methane should increase in concentration and the hydrogen decrease after its addition. So the choice B indeed shows the hydrogen decreasing slightly and the methane increasing slightly. And notice that the ratio is preserved. The hydrogen seems to have decreased 3 times as much as the methane increased. So choice B is the best answer. A couple of free response questions to finish with. We've got a gas syringe containing the pale brown mixture of N2O4 and NO2. Remember that N2O4 is essentially colorless, while NO2 is brown colored, and that's why the mixture is a pale brown color. We keep the volume constant, the temperature is raised to 35 degrees, the brown color becomes more intense. If the brown color is becoming more intense, then our equilibrium is shifting forwards. If it's shifting forwards because of increasing temperature, heat must have been on the left side, and that means this reaction was endothermic. Now, how would you explain that in an acceptable way on an AP exam for free response? Well, what I would have said here probably first of all is note that there was a forward shift in equilibrium because of the darker brown color. I would have indicated therefore that Kc is larger at the higher temperature. Therefore, the forward reaction is endothermic. Okay? Raising temperature causes Kc to increase for an endothermic process. Keeping the temperature at 35 degrees, the plunger is pushed in to halve the volume. What would we expect to see? Well, if we halved the volume, if we squeezed the gas into a smaller volume, the first thing we should note is that it will get darker. It's going to get darker not because of an equilibrium effect, but simply because we're squeezing the brown gas into a smaller volume. It becomes more concentrated. Now we can consider the equilibrium. As the volume decreased, the pressure inside increased. the system's going to try to lower the pressure by reducing the amount of gas, and that means it's going to shift backwards from the NO2 back to the colorless N2O4, so then it will get paler. It will fade in color after getting darker. So there's an initial darkening simply because the gas was squeezed into a smaller volume. Then, as the equilibrium shifted backwards to reduce the pressure, the system will get paler colored. This time we have the same system. The volume and the temperature are kept constant, while N2O4 is added at time t. What would we observe? Well, the volume doesn't change, so there's not going to be that effect we just saw earlier about a darkening or lightening because of the volume changing. But if we add some N2O4, the system's going to shift forwards because of an equilibrium effect, and that will create a darker NO2 produced. Therefore, we can say the mixture gradually gets darker. Which of the following graph shows the concentration of NO2 varying? The NO2 would have started off, then the NO2 would have gradually increased as a result of the shift in equilibrium, so C is the best answer. Calculate Kc for the third reaction. This is one of those questions where you have to derive the third reaction from the two above. So CO2 plus hydrogen makes water and CO. I want to get this equation by rearranging and perhaps multiplying the equations above by some numbers. So I want one CO2, not two of them. So I'm going to take the second equation and just rewrite it, but I'm going to multiply everything by 1/2. So CO plus half O2. Since all I did was multiply by 1/2, the Kc now is the square root of 1.3 times 10 to the minus 10. The first equation, so now I've got my CO2 where I wanted it, I've got my CO where I wanted it. The first equation has two waters on the left, and I want one water on the right. So I'm going to take the first equation and reverse it and multiply by 1/2. So 1 hydrogen, half oxygen, 1 water. Because I reversed it and multiplied by 1/2, its Kc is now 1 over the square root of 1.6 times 10 to the minus 11. Now just verifying that when I add these together, the oxygen cancels, and indeed I get the equation I wanted. Then the Kc that I'm looking for is the product of those two Kc's, which will mean it's the square root of 1.3 times 10 to the minus 10 over 1.6 times 10 to the minus 11, and I'll just let you grab a calculator and evaluate that. So remember that when you multiply an equation by any number, in this case we multiplied by 1/2, you raise Kc to the power of that number. So Kc to the power of 1/2 is square rooting it. If we reverse an equation, then Kc, we take the reciprocal of it, because what used to be products are now reactants. The Kc expression is flipped over. And finally, when you add equations together to get a net equation, Kc for the net equation is the product of the Kc's that you were adding together, for the reactions you were adding together. We've got bromine dissolved in water, and this equilibrium established. In an experiment, some dilute sodium hydroxide and then some dilute hydrochloric acid are added. Explain the observations with Le Chatelier's principle. Adding sodium hydroxide, the hydroxide ion will react with the hydrogen ions in the equilibrium to produce water. So the hydrogen ion concentration will be decreased when we add sodium hydroxide. Therefore, the rate of the reverse reaction decreases. The system shifts forward as a result, now that the forward rate is larger than the reverse rate, and we will see a fading color and eventually become colorless. On the other hand, if we, in the second step, add hydrochloric acid, the reverse happens. We increase the concentration of hydrogen ions. That will increase the rate of the reverse reaction, and now the reverse reaction rate is faster than the forward. We see a reverse shift, and the color becomes yellow-brown. All right, we can see here that at low temperature, this reaction equilibrium system looks blue, and at a higher temperature, it looks green. Why would that be, and is the reaction endo or exothermic? The fact that it looks green at the higher temperature tells me that the reaction is shifting forwards, so that we have a mixture then of the yellow product and some leftover blue. So raising temperature saw this reaction shift forwards. That means raising temperature caused more product to form, so raising temperature caused Kc to increase. Kc increases when you raise temperature for endothermic processes, so this reaction was endothermic. Adding a catalyst will increase the rate of the forward reaction. It will increase the rate of the reverse reaction, but it'll do so equally, so there's no change in equilibrium, and there's definitely no change in Kc. The reaction was exothermic. If we raise the temperature, we will increase the two rates, forward and reverse. But in an exothermic process, the reverse reaction, which is then endothermic, increases to a greater, the rate increases to a greater extent. So the reaction shifts to the left, backwards. Kc then decreases. I guess I'll use my minus symbol. No, I won't. Let me just fix that. I'm going to use a 0 symbol to represent no change. No change. And here my Kc gets smaller, so negative. Increasing the pressure here will cause the equilibrium to shift in the reverse direction to lower the amount of gas. So therefore the rate of the forward reaction is decreased, the rate of the reverse reaction is increased, and the position of equilibrium goes backwards. However, Kc does not change because we have no change in temperature.